Good evening, everyone. My name is Prateek Sahni, and I'm going to share my summer project titled Non-Invasive Fetal Electrocardiogram Extraction from Trans-Abdominal Maternal Sensors that I worked on with Dr. William P. Pfeiffer of the Department of Psychiatry and Developmental Neuroscience at Columbia University College of Physicians and Surgeons. So here's some background. Measuring the fetal heart condition during pregnancy is of paramount importance. Standard fetal monitoring using Doppler ultrasound provides only general patterns of fetal heart rate and can be inaccurate and unreliable. Abdominal recordings of the fetal electrocardiogram are an upcoming and promising new methodology to assess fetal health and well-being. Electrical signals recorded from the maternal abdomen are affected by interferences from the maternal electrocardiogram, or MECG, and muscle activity. A wireless fetal electrocardiogram monitor, Monica AN24, as shown here, is not commercially available and has potential to provide more than just average fetal heart rate information. The objective of my study was to evaluate the feasibility of extracting fetal electrocardiogram from the electrical signal obtained from the maternal abdominal sensors using Monica AN24. On to the methods. 5 surface electrodes were placed in a standardized fashion over the mother's abdomen and connected to the Monica AN24 monitor. These electrodes create 4 separate channels of composite recordings that include the fetal electrocardiogram, maternal electrocardiogram, and movement. Data was collected for 20 to 30 minutes on each subject and downloaded onto a computer. Monica AN24 does not give the user access to process individual electrophysiological signals, especially the fetal electrocardiogram and the maternal electrocardiogram. The raw signal, as shown on the top panel of this figure, was reviewed and analyzed using the Monica DK software, which is a branch of the Monica AN24 device. The resultant analysis, as shown on the bottom panel, includes the fetal electrocardiogram and the maternal electrocardiogram without the movement signals. Custom software was then used to extract 4 channels of the fetal electrocardiogram from the composite signal. Signal averaging algorithms based on the best fetal QRS complex, which is this wave, were used to obtain a representative fetal electrocardiogram. This fetal electrocardiogram was now ready for waveform analysis, including the P, the QRS, and the T waves. Results. We were successfully able to extract reliable and accurate fetal electrocardiogram from 95% of the electrical signals obtained transabdominally in the first 1,000 pregnant mothers in an ongoing study. A typical fetal electrocardiogram, as shown here, can be utilized to calculate true beat-to-beat fetal heart rate, quantify various cardiac intervals, such as the PR and the QT intervals, as they're shown in the graph, and track fetal electrocardiogram morphology and amplitude changes. We conclude that it is feasible to extract reliable and accurate fetal electrocardiogram from the electrical signal obtained from the trans-abdominal maternal sensors using a simple, comfortable, inexpensive, and most importantly, non-invasive methodology. We speculate that widespread access to the fetal electrocardiogram could potentially help in assessing fetal well-being during pregnancy and labor, substantially improve the diagnosis and treatment of fetal rhythm disturbances, and greatly impact the field of fetal cardiology. Additionally, calculation of various fetal electrocardiogram waveforms and intervals would allow for the diagnosis of fetal arrhythmias, rhythm disturbances, congenital heart blocks, and long QT syndrome, a known cause of sudden cardiac death and sudden infant death syndrome. Further, I would like to thank Dr. Cox, Dr. Pfeiffer, and Dr. Matejko for the support for this presentation. Thank you.